The calculus, one of the most basic and fundamental tools of modern mathematics. Two men can rightly claim to have invented it, Isaac Newton and Gottfried Wilhelm Leibniz. Newton actually discovered his calculus first, in 1665 or 1666. Leibniz made his own independent discovery of it some 10 years later. However, neither man saw fit to publish what they'd found for some years after that. What's really fascinating is that the original writings recording the discoveries of both of these men are preserved. In the University Library in Cambridge, we have the notebooks that Newton kept between 1665 and 1667. And in Hanover, Leibniz's notes from 1676 are preserved as well. They provide a fascinating glimpse into the process of mathematical discovery that both of these men used, and it's really exciting to be able to study them. We start our story with Newton. Newton was a student at Trinity College, Cambridge, and in January 1665 he took his degree and became Bachelor of Arts. There then followed 2 years of intense work in which many of Newton's basic ideas on the calculus, as well as optics and gravitation, were formed. We shall restrict ourselves to his mathematics. In May 1665, Newton was working in Cambridge. He was rapidly mastering and improving on the methods of Descartes and Hooder for finding tangents. The contemporary way of finding a tangent to a polynomial curve, that is, a curve with a polynomial equation, was as follows. To find the tangent to this curve at the point P, look at circles with centres on the x-axis passing through P. Most circles will cross the curve at P and recross it at another point, but one circle will just touch the curve at P. The line from the centre of this circle to P is called a normal, and the line at right angles to this normal through P is the tangent to both the circle and the curve. Hooder, who was a smart mathematician, had developed a cunning way of finding the centre of this circle, which used the following trick invented by Fermat. In general, a circle cuts the curve in 2 places. Suppose this distance is O. Now find an expression for the distance d of the centre of the circle from some convenient reference point in terms of O. Finally, assume that O actually has a value of 0. The procedure gives a value for d. And so the centre of the circle and the normal CP can be found. This method was reliable in practice, but it could be complicated to apply. This is what Newton called his waste book, in which he kept entries on a vast number of different topics. And these are the mathematical pages which have been taken out and rebound. Here, on the 20th of May 1665, he made a note which makes it clear that he had mastered these techniques for finding normals and tangents. On this very page he writes that he has a universal theorem for tangents to crooked lines. Now, Newton was well aware that tangent problems and area problems were inverse to one another, so every time he solved a tangent problem, he'd solve the corresponding area problem, and he wrote that up as such. Here, in this little book, he presents a method whereby to square those crooked lines which may be squared. Squared means area. It was the standard terminology of the time. And here, he starts writing down the results. 3x squared equals ay, the parabola, has square or area x cubed over a. 4x cubed equals a squared y, has square or area x to the 4th over a squared, and so on down the page. Given the equation of a curve, Newton starts by writing out tables of values for the area under the curve. So by summer 1665, Newton has mastered the techniques of Descartes and Hooder for finding tangents to curves. He's also used the inverse relationship between tangents and areas to write down the areas under lots of curves. And he finishes by writing down a result which summarizes the pattern that he has noticed. if ax to the m equals by to the n, then nxy over n plus m is the area under the curve described by y. In the autumn of 1665, Newton returned to calculating tangents. Calculating tangents is generally Newton's main aim, but now he had switched his attention to mechanical curves. Mechanical curves are curves defined by motion rather than by polynomial equations.
The most famous of these is probably the cycloid. A cycloid is the path traced out by a point on the circumference of a rolling circle. A tangent to this curve can be thought of as the instantaneous direction of motion of a point as it traces out the curve. For the cycloid, this direction of motion can be worked out as follows. At this instant, the point on the circumference of the circle is moving with equal speeds in the direction the circle is rolling and along a tangent to the circle. Combining these two speeds using the parallelogram rule gives this direction of the tangent. This idea of instantaneous direction of motion was not new. Kepler, Galileo, Torricelli and Roberval had all exploited it, but none had ever really understood it. Newton dived in, copying much of what had been done before and making the same mistakes. Following the traditional method of the time, a point on an Archimedean spiral would appear to have velocities in these two directions. So combining the two gives the tangent. For the ellipse, the length a plus the length b is a constant. So, at any instant, the speed with which a is increasing must equal the speed with which b is decreasing. So using the parallelogram law, the diagonal gives the direction of the tangent. These sort of constructions do indeed give tangents, but for completely wrong reasons, as was shown when applied to the quadratrix. The quadratrix is formed by tracing the path of the point of intersection of a horizontal line moving downwards with uniform velocity and a line rotating with constant velocity about the origin. The method used for the spiral and ellipse says that the tangent at this point should be a combination of speeds in these two directions. It clearly didn't work. Several mathematicians, including Descartes and Roberval, attempted to modify the method, but none seemed to work really satisfactorily.
However, when Newton had perfected his method some months later, he returned to this problem and worked out what the correct construction should be. This work with mechanical curves seems to have given Newton a new way of looking at all curves. This is how Newton now perceived of a curve.
Simultaneously, 2 points move along in the x direction and along the y direction. The distance moved along the y-axis at any time is related to the distance moved along the x-axis by some relationship which may be a polynomial equation, but could also be some sort of mechanical link. So, by interconnecting these two movements, a curve would be drawn. But what Newton was interested in was working out the ratio of the velocities of these 2 points. He knew what the curve was, however it was defined. So he knew how any distance along one axis was related to a distance along the other axis. But Newton's concept of the way this curve was generated was by movement. And what Newton wanted to know was how the velocities of the 2 points were related.
This was a fundamental perception of the problem, and on November the 13th, 1665, it led Newton to give a new method for finding tangents. He starts by going back to curves he knows and showing how to find the ratio of the velocity q of y to the velocity p of x. Basically, he lets an infinitely small amount of time elapse in which the point moves from xy to x plus little o, y plus little o q over p. He writes, what is x and y in one moment will be x plus little o and y plus little o q over p in the next. So x plus little o, y plus little o, q over p, is a point on the curve. That means he can replace x by x plus little o, y by y plus little o, q over p in the equation of the curve. And then let little o take the value 0, a perfectly systematic method and not dissimilar from what we do today. Newton seizes on the idea that the ratio of q over p, that is the ratio of the velocities, will give him the direction of the tangent. He then writes this very important page, in which he claims that the method is completely general, to draw tangents, he says, to crooked lines, however they may be related to straight ones. Now he's completely certain that his method will give him the tangents at all curves and all points, and he says, hitherto may be reduced the manner of drawing tangents to mechanical lines, see folio 50. Folio 50 was his earlier and incorrect method for drawing tangents to mechanical lines. So now he has a method for finding tangents to all curves. In particular, he can find the tangent to the quadratrix, the first time this had been done in complete generality. So this page marks an important step in the development of the calculus. Not only is it completely general, but when it's applied to curves given by polynomial equations, it allows Newton to use the rules he had before for finding tangents, but without the need for Hooda's complicated calculations. It's still mathematically imprecise, though. Not only is there the question of relating geometrical constructions for tangents to instantaneous velocities, there's the business of relating velocities to movements in infinitely small amounts of time. Through the winter of 1665, Newton ponders the concept of velocities. Then, in May of 1666, he starts to write up his results. Here he says, instead of the ordinary method, it would be convenient and perhaps more natural to use this. Namely, to find the motion of any line or quantity. And then, in this little tract of October 1666, he pulls all his results together. Not only are the proofs or demonstrations more explicit, but the whole thing is more coherent. And by putting it all down in one place, he may have intended to let other people see it. He still doesn't give his velocities any special name. They are what he will later call fluxions, but that has to wait for yet another rewrite, that one of 1671. But this tract of October 1666 contains Newton's first presentation of the basic ideas of the calculus.
Our story of Leibniz begins in London in 1673. In January of that year, he presented to the Royal Society a calculating machine he had invented. Incorporating several novel features, he was elected a Fellow of the Royal Society on the strength of this invention.
All his life, Leibniz worked to mechanize all reasoning processes. He wanted to formalize the rules of logic so that any logical argument or mathematical proof could be produced by a machine. Leibniz saw the calculating machine he took to the Royal Society as just the first stage in the development of such a logical machine, and all his life he worked to improve his calculating machines. This is the sixth. Begun in 1690, it was not completed until after his death, some 30 years later. These ideas of Leibniz are important, since they do much to explain his way of working and the particular care he went to invent a powerful and flexible notation for his calculus. Leibniz's invention of his calculus grew out of his study of contemporary mathematical problems, in particular area and tangency problems. So how were they studied at that time?
It was under the guidance of Christian Huygens in Paris that Leibniz was to learn his mathematics. At that time, it was quite usual to think of an area as somehow made up of lines. This was a tradition going back to Cavalieri, and more recently defended by Pascal. So, to compute an area, you considered all the ordinates. The notation, deriving again from Cavalieri, was omn L, from the Latin omnia meaning all, L standing for the ordinates. Why is this reasonable? If we want to compute this area, we would probably pick ordinates a fixed amount, delta, apart. We could then approximate the area by rectangles. Now, each of these rectangles has an area of ordinate Li times delta. So the area we seek is approximately the sum of all these products. This sum can be rewritten as the sum of the LI's times delta. We'd finish our calculation by letting delta get smaller and smaller, giving better and better approximations of the area. What Leibniz believed was that the area was made up of all the ordinates taken infinitely close together. When you did this, he argued, the sum was of all the ordinates, and that gave you the area directly.
So to Leibniz, to find an area is to find on L of a figure, a highly geometric procedure. But he wanted to systematize mathematical reasoning. To see how he proceeded, we're in the fortunate position of being able to go to the Landesbibliothek Hanover, where tens of thousands of pages of his writings are collected. With the help of the staff here, who are engaged in the lengthy business of publishing them, we are able to pick out just the few pages we need. Here, for example, is a crucial one, dated the 26th of October, 1675. Leibniz wants to find the area under this curve. So that you can see what's going on, we've enlarged it for you and turned it round like this. Leibniz wants to find the blue area. He noticed that it was the area of the whole rectangle minus the yellow area and wrote down this formula. This is the blue area, that's his sign for equals. This is the area of the whole rectangle, and that's the area of the yellow bit. Leibniz then applied this result to a over x and obtained a result connecting logarithms with the areas of hyperbolic sectors. The result was not new, but Leibniz may well have been surprised by how easily his new methods obtained it. Now on the next page, written only 3 days later, Leibniz is investigating rules for omnia. He writes that omnia yl over a cannot be said to be equal to omnia y times omnia l, nor is it y times omnia l. Then he decides that writing omnia gets in the way. On the next side, he says, it will be useful to write this symbol for omnia and this for omnia l, that is, the sum of all the l's. To Leibniz, this was just the long script S for summa, or sum. But of course, we recognize it immediately. This is the first occurrence of the integral sign. Leibniz, ever keen for the most appropriate symbol, introduced on the 29th of October, 1675, a sign that remains unchanged to the present day. He then proceeded to find some rules for his new symbol. Here he writes omnia x is x squared over 2. Here omnia x squared is x cubed over 3. And here that omnia a over b times l is equal to a over b times omnia l, whenever a over b is a constant. With the introduction of his new symbol, Leibniz is, of course, dealing with problems of area.
But areas and tangents, as Leibniz knew, were related problems. If the sum of the ordinates made up an area, the difference between two ordinates represented the increase in the curve over the interval. And when the ordinates moved infinitely close together, the tangent was produced. So, in Leibniz's mind, was the realization that areas were summations and tangents differences.
And here we see Leibniz saying just that. He writes, given L related to x, we are to find omnia L. What can now be done from the contrary calculus, evidently, is if omnia L equals y over a, we may set L equals ya over d. Consequently, just as omnia increases dimensions, so does d diminish them. Omnia signifies sum and d difference. Here, Leibniz introduced the d symbol, d for difference, as he said. But he wrote it underneath because just as omnia increases dimension, it goes up from lines to areas, so his opposite operation must reduce dimension. But Leibniz didn't stick to this notation for very long. In another note, this one written 12 days later, the d moves upstairs. As he says in a margin, dx is the same as x over d. That is, the difference of two neighbouring x's. This is a very exciting moment. For the first time, the two basic symbols of the calculus exist, and Leibniz is looking for rules for their use. Here he writes d of x times y is equal to d of xy minus x dy, which we can immediately rewrite as x dy plus y dx equals d of xy. So here, in the space of 3 weeks in autumn 1675, we see the foundations of the Leibnizian calculus laid down. Once the discoveries were made, it's interesting to see how Leibniz proceeded with them. Here's a document written in mid-July 1677, which makes it clear that Leibniz is looking for a way of casting in his discoveries in a way that makes them amenable to a universal, automatic process of reasoning. He writes, "But to explain my ideas neatly and succinctly, I am obliged to introduce some new characters and to give them a new algorithm. That is, special rules for their addition, subtraction, multiplication, division, powers, roots, and equations." So he's cast his discovery in the form of rules for d. Here is the rule for multiplication, d of a product, and here, d of a quotient. So to sum up, it's interesting to compare our two central characters as they stood in the late 1670s, their great calculus, or should I say calculi in the plural, as yet unpublished. When we make such a comparison, several interesting points of agreement emerge, as well as several interesting divergences. Similarities first. Above all, both calculi are about geometric properties of figures, areas, and tangents. And both men went a long way to automating their findings and subjecting the calculus that they discovered to rules. But there are also several interesting divergences. Newton spoke of fluxions. Infinitesimal increases in a variable were the means he used to find his fluxions. And from the first, he was always attracted to the idea of motion, of change in time as a way of expressing mathematical ideas. And although his thoughts on that topic grew more profound as the years went by, he was always wedded to the language of motion. Leibniz talked of differentials, of infinite linear points, of curves being made up of infinite-sided polygons. No motion here. Rather, a bold geometrical analogy, which, whatever else, yielded valid rules for what came to be called differentiation and integration. Indeed, the rules which Leibniz found are more basic to his way of thinking mathematically than were the equivalent rules found by Newton. It's hard to overestimate the power of the calculus as Newton and Leibniz described it. Indeed, it can be argued that when they came to publish their findings in the late 1680s, mathematics received the greatest increase in its power since the time of the Greeks.